Module 7.1, Quality Assurance in Radiochemical Analyses. Overview of requirements for the radiochemistry laboratory. This module provides an introduction to the concepts of quality assurance and quality control as needed for a successful analytical program in the radiochemistry laboratory. At the end of this module, you should be able to state the overall objectives for measurement quality represented by the acronym PARCCS. You should know which documents list the requirements and provide the guidance for implementing the EPA Quality System for laboratories analyzing drinking water. List the EPA Quality Assurance Program requirements for a laboratory's organizational structure, training, documents and records, controls, and data reporting activities. Describe the EPA Quality Control requirements for quality control samples, the parameters to be monitored, and the proper use of control charting. List the 4 areas of concern for counting instrumentation QC and describe how they are addressed for detectors, liquid and solid scintillation counters, gamma spectrometers, and alpha spectrometers. Keep in mind that these are the basics for a QA/QC program and that additional requirements exist and should be identified by reviewing the documents listed herein as references. These two concepts are often melded together. The definitions provided on this page come from the MARLAP. The overarching program is quality assurance, and the quality control program is a portion of that quality assurance program. One way of identifying the responsibilities ascribed to these programs is that quality assurance establishes long-term programmatic requirements, while quality control is used to ensure that those requirements are met on a daily basis. The figure on this slide provides an overview of how quality assurance melds into quality control. The management of the process needs to be established in a written document that is specific to the laboratory. The Quality Assurance Plan, or QAP, for each laboratory should identify each of these processes, as well as others, and how they support the overall product of the laboratory, data. Each member of the laboratory should understand the connection of each of these parts of the process to the overall production of the data. The acronym identified on this slide, PARCCS, or PARCCS, describes the relationship of the laboratory process to the final reported data. The figure on the right depicts the qualities of the first 2 terms, precision and accuracy. Ideally, the values obtained from the laboratory's analytical process should be precise and accurate, with the precision arrows also centered on the bullseye of the target. Representativeness means that the final analytical result must be representative of the whole sample that was received by the laboratory. The results reported must be complete, each result reported with a stated uncertainty and any other data reporting requirements that were requested by the client. The results must also be comparable to other aliquots of the same sample analyzed either by the same method or another approved method for that analysis. Comparability can be shown by analysis of duplicates and matrix spikes. Finally, the results should have the sensitivity, sometimes referred to as a detection limit, that was requested by the client. For drinking water analyses, this means that the sample-specific detection limit should meet those required in 40 CFR. Listed on this slide are several documents that provide guidance on how to establish a quality assurance program. The analytical requirements for the radiochemistry laboratory and analysis of samples for drinking water are cited in 40 CFR 141. Keep in mind that when regulations change, they will be published in the Federal Register, and 40 CFR will be updated in the next annual revision. The EPA provides additional guidance for the chemistry laboratory in the certification manual. This is the central document that laboratories should use when planning their programs. The manual provides details on frequency of quality control checks, documentation for procedures and data, training for analysts, laboratory organization, and several other areas listed here and also identified in the document itself. Laboratories also should use the certification manual for guidance when revising their quality assurance program. As stated in this slide, the Quality Assurance Plan, or QAP, needs to specify the details of each of the areas required for laboratory operations. This plan is the framework that provides the long-term continuity and consistency of laboratory operation and ensures that there is a continuity of quality measures from sample receipt to data reporting. The Quality Assurance Plan is a requirement for each laboratory. The regulations for this program are contained in 40 CFR and may change as a function of time. EPA publishes a certification manual that provides detailed guidance on the various areas necessary for a successful QAP. Instruments used for radiochemical measurements must meet quality requirements of the method being used and should meet applicable industry standards for its operation. Operational requirements for each instrument must be addressed in a standard operating procedure, or SOP. Instruments must be calibrated prior to using them for making analytical determinations. Their stability must be checked at frequencies identified in the standard operating procedure, and acceptability criteria should be established prior to use. The electrical power for the instruments should have the properties noted in the bullets here. The maintenance requirements for each instrument should be in accordance with the manufacturer's operating manuals, and these manuals should be readily available. The table on this slide identifies the types of quality control samples required for each batch of samples and the frequency with which these QC samples should be performed. The certification manual has additional information regarding the requirements for these samples. When samples such as these meet the predetermined acceptance criteria, the results provide assurance that the method is working properly and the analytical results are reliable. The parameters that identify whether or not the control samples meet predetermined acceptance criteria are shown here. The certification manual gives the values for these acceptance criteria. Instrument quality control checks, instrument background and efficiency are performed prior to and succeeding each batch of samples. The requirements for the quality checks on the instruments are shown here. Each instrument has different requirements for these checks. For example, when only one high-purity germanium detector is in use, the requirements for daily checks may supersede those for batch quality control checks when the analysis of the batch spans more than one day. A control chart plots the individual datum for a particular control parameter. The control chart has an x-axis where the date or chronological QC sample number is plotted, and a y-axis where the analytical value or an equivalent measure of that value is plotted. 5 horizontal lines are usually placed on each chart. 2 lines are for control limits, 2 lines are for warning limits, and 1 for the central value line. The central value line is the best estimate of the true value. This may be based on a standard value or the average of at least 20 independent measurements of a standard. The warning and control limits are symmetrically placed around the central value at 2 and 3 sigma. Every quality control value that is plotted should be viewed not only in terms of being within the control limits, but also to see if the method is producing results in a normally distributed fashion. The control chart seen on this slide is indicating that the last 7 successive data points are trending in one direction. This is not a normally distributed pattern of results. Although all the points are within the control limits, this trend is worthy of an investigation as to its cause. Some values that are used in the assessment of analytical measurements vary by very small amounts. When such a parameter is used in evaluating instrument control, it is sometimes more reasonable to use a tolerance limit rather than a control limit. The difference is that a tolerance limit is a change in value up to which the final measurement will be unaffected. A tolerance limit is usually established based on best professional judgment. The example shown here is for the full width half maximum of a gamma ray peak. If we were to measure the full width half maximum of standard at 661 keV for cesium-137 many times, we would likely calculate a 3 sigma control limit of 1.7 plus or minus 0.1 keV. However, when the software algorithm calculates a peak area, there would be little difference if the peak were 1.7 or 1.9 keV wide. For this type of parameter, a tolerance limit is the best method to use as a control parameter. Any analyst who performs drinking water analysis must show that they have the capability to accurately and correctly apply the method for specific analyte being measured. This is shown during the demonstration of proficiency. It is an annual requirement for each analyst for each method. It may be demonstrated by repeating the original studies used for proficiency or by documentation of successful batch analyses, including quality control samples over the course of the year. The analyst must use quality control analyses both for the instrument and for the method. Most of these analyses are to be plotted on control charts that have predetermined limits of acceptance. The frequency of these control samples is described in Chapter 6 of the Certification Manual. The acceptable performance of these control samples ensures that the PARCCS parameters for analytical process will be successful. Each of the instruments that are used routinely in radiochemical analysis, alpha spectrometry, gamma spectrometry, gas proportional counting, and liquid scintillation, are to be used only after their accurate operation has been successfully demonstrated. Each instrument requires an initial setup, establishment of performance using QC data, calibration, and checks of operation. These individual performance concerns may be performed in different order for each instrument. Background counts are used for two different purposes. The instrument background is used for subtraction from the gross sample counts and should be for at least as long a time period as the sample is counted. The frequency with which a background subtraction count is determined is stated in the QAP and must be the most restrictive for all analyses that it was used for. It is important that the background subtraction counts be performed with a vessel equivalent to that used for sample analysis so that the background is reproducible for the sample subtract background. Gas proportional counters are the workhorse of the radiochemistry laboratory. The instrument QC samples are used to check the validity of the detector calibration on a continuing basis. The quality control source geometry should match that of the samples and standards. The quality control source should be made from a separate source than the standard used to calibrate the detector. This provides an independent check on the calibration. Some instruments may have a separate check source used for validation of the detector operation. These checks should also be recorded on a control chart to ensure instrument stability. Two types of scintillation counters are routinely used in the radiochemistry laboratory. The liquid scintillation counter will require the establishment of background laboratory control sample and efficiency checks prior to it being used to generate analytical data. This detector also uses a manufactured sealed, unquenched check source provided by the instrument manufacturer. The most commonly used source and analysis that the liquid scintillation counter is used for is tritium. Not only does the sealed source need to be decay corrected, but the standards and samples as well. One of the challenges is to establish a control chart so that the decay of the laboratory control check is taken into account, as are the central value, control, and warning limit lines. Lucas cells are the other type of scintillation counter used in the radiochemistry laboratory. Each cell must be calibrated with its own photomultiplier tube. Each PMT and cell combination must be checked and used together as the calibration is geometry specific. Since each cell is used to trap the radon gas that is purged from the radium solution, the decay products of radon are also trapped in the cell. The background for the cell plus the PMT must be determined and plotted immediately prior to each use. Gamma-ray spectrometers are usually used to analyze samples without any chemical separations. This does make the sample geometry and the sample density important parameters. They must match exactly the geometry of the standards and match closely the density of the standard. The detectors here too need to be checked for background and efficiency. They also need to be checked for resolution, or the full width half maximum of peaks, and the location of the central peak. These are all important control parameters that, when in control, provide evidence that the detector is working properly. The alpha spectrometer is used after chemical separations. However, the checks for background, efficiency, centroid location, and full width half maximum of standards are equally important. These parameters should be control charted as they are for gamma spectrometry. Each instrument should be set up in accordance with the manufacturer's specifications. The efficiency and background for each detector should be verified with the specification provided with the instrument. Once the instrument is set up and a qualitative check of its performance has been done, a calibration must be performed using NIST traceable sources. Following the calibration, quality control checks of the instrument should begin and a control chart for each parameter established. Environmental conditions in the laboratory, such as vibration and light exposure, may potentially affect the QC measurements and should be taken into consideration when evaluating QC data. The instrument should be checked on a routine basis for all parameters that feed into the final analytical values. The certification manual contains guidance on the minimum checks that should be performed on each instrument. This module has provided you with some of the basic concepts of quality assurance and quality control. You should be able to distinguish between these two functions and state why each plays an important role in producing data that is reliable and defensible. You should be able to use the guidance provided by the EPA Certification Manual on quality control analysis for sample batches and instruments, as well as other quality functions for the laboratory.